In this lecture, we will talk about Markov chains. In fact, the Markov chain is a random process. The theory of a random process was first established to study the fluctuations and noise in physical system. Moreover, the random process provides useful models to study the statistical physics, communication and control, population growth, and management sciences, and so forth. So here, first let us talk about random process. A random process or stochastic process can be described as it is the collection of time function or a signal corresponding to various outcomes of random experiment. Also, the collection of random variable observed at different times. The examples of the random process in communication system are such as noise, channel noise, information generated by a source, and interferences. Also, the intensity of sun measured by every day can be described by random process. So here x of t represent the intensity of sun at daytime. So t is the time for daytime. It represent time, so corresponding to different time the intensity is different here. So here t, which is greater than 0 and less than some interval, that is capital T. Now let us talk about Markov chain process. Sometimes we are interested in how a random variable change over time. So we want to investigate some random variable that change over time. So also the study of how a random variable evolve over time include stochastic process. And explanation of this stochastic process, in particular a type of stochastic process, is known as Markov chain. So if we are interested how random variable change with time and how these random variable evolve over time, so to study this random process, we choose a type of random process which is known as Markov chain. So what is Markov chain? Its definition: a discrete time stochastic process is a Markov chain if for time t is equal to 1 to 1, 0, 1 up to so on, up to all states. So it can be described by the conditional probabilities. So here the conditional probability, so this can be described by the conditional probabilities. Now taking the left hand side of this equation, so the probability at time t plus 1 is equal to state I t plus 1. So here for time 0 it has a state I0. For time 1 it has state I1. So for time t it has state I. So on the right hand side it can be described as the conditional probability. For time t plus 1 it has state I plus 1. For given time t it has state I of it has state I. So this equation says that the probability distribution of the state t plus 1 essentially depends on the state t and does not depend on the state the chain passed through the through on the way to it at time t. So it only merely depend on the on the uh, on the state t. सो हम कह सकते हैं कि जो स्टेट t+1 है ये डिपेंड करती है स्टेट t पे, ना कि इससे जो पहले वाली स्टेट्स थी, सपोज t-1 या t-2, उन पे नहीं डिपेंड कर रही। स्टेट t+1 जो है डिपेंड कर रही है स्टेट t पे। So in our study of Markov chain, we make further assumption that for all state I and j and all time, the probability, conditional probability for time t+1 is equal to j for given for time t, its state I is independent of time. The assumption allows us to write the probability for time t+1 is equal to j for given for given time t, it has state I. So this can be described as the probability of p sub ij, where p sub ij is the probability that given the system is in the state of I at time t, and it will be in the state of j at time t+1. ये जो probability है ये किसी सिस्टम की अगर स्टेट ये probability हमें देता है जब स्टेट आई होगी एट टाइम t पे, और जो स्टेट j है दैट विल बी एट टाइम t+1. So if system move from state I during one period to state j during the next period, we call the transition from I to j. अगर सिस्टम मूव करता है I स्टेट से j स्टेट तक तो हम क्या कहते हैं, हम इसे कहते हैं ट्रांजिशन फ्रॉम I to j हैज अकर्ड. सो p sub ij's are often referred to the transition probabilities. इनको हम ट्रांजिशन प्रोबेबिलिटीज भी कहते हैं जब सिस्टम I स्टेट से j स्टेट पे मूव करता है. These are called the transition probabilities of the Markov chain. This equation implies that the probability law relating to the next period state to the current state does not change over time. It is often called stationary assumption, and any Markov chain that satisfies it is called stationary Markov chain. We also must define q sub I to be the probability that the chain is in state I स्टेट पे जब होगा तो उसकी प्रोबेबिलिटी है q sub I एट टाइम t इज इक्वल टू इनिशियल जो है उसकी प्रोबेबिलिटी qi है विच इज एट टाइम 0. इन अदर वर्ड वी कैन से द प्रोबेबिलिटी एट टाइम t इज इक्वल टू 0, जो स्टेट I है उसकी प्रोबेबिलिटी इज q sub I. वी कॉल द वेक्टर, जो हम ये वेक्टर this vector the q vector which is from q1 to q2 up to qm, so it provides the initial probability distribution for the Markov chain. Next, in most application the transition probabilities are displayed as an m cross m transition probability matrix. The transition probability matrix को हम लिख सकते हैं p1 ऑफ 1 से मुराद है कि पहली स्टेट पे अगर हम हैं उसकी प्रोबेबिलिटी अगर पहली स्टेट पे हैं, p1 2 से मुराद ये है कि पहली स्टेट से अगर हम दूसरी स्टेट पे मूव करते हैं, I से J पे मूव करते हैं, और J यहाँ पे 2 है, और सो ऑन. p1 ऑफ m से मुराद ये है कि अगर J हमारे पास m है, हम स्टेट 1 से स्टेट m पे मूव कर रहे हैं, तो इन सिमिलर फैशन अगर हमारे पास pm1 से मुराद ये है कि I स्टेट जो है m है और J 1 है, तो m से 1 पे मूव कर रहे हैं. ये ट्रांजिशन मैट्रिक्स जो है स्टेट को डिस्क्राइब करने के लिए यूज़ करते हैं. Also, this transition probability matrix describe the one state to another state. If we want to move from one state to another state. Furthermore, the sum of the probability of each row is equal to 1. So in this case, when j is equal to 1 to m, so by taking the sum of these probabilities, which is equal to 1. Also, this initial probability distribution vector, if we take the sum, the overall probability would be equal to 1. Now let us talk about some example. Let's three boys A, B and C throw a ball to each other. The throwing habits are as follow. A always throw the ball to B. A always throw the ball to B. B always throw the ball to C. C is twice as likely to throw the ball to A as B. So first, so here write the transition. We have to write the transition probability matrix and classify its state. So transition probability matrix, if we suppose the state as this is A, this describe A, this describe B, state B, this describe state C. So first we are at state A, so it is sure that A always throw ball to B. So it has the probability 1, and it does not throw, A does not throw the ball to C. So if we take the sum of these probabilities of this row, it must be equal to 1. Now in the second row, the ball is now with the B. Now the B will throw the ball to C. So we can write in this way. So here the probability will be 0. B will not throw to A. B will throw to C. So here the probability is 1. Now C is twice as likely to throw the ball to A. So I can write it as this is 2x x and to B. So if he throw the balls, if x probability, x is the probability, it throws the ball, C throws the ball to B, then it would be 2x for A. So it has twice, C has twice as likely to throw the ball A as B. So the sum of the probabilities, we know that for each row is equal to 1. So by adding these 2x plus x, this must be equal to 1. So the x is equal to, by solving this equation, the x is equal to 1 over 3. So I will incorporate here. So here the probability that C will throw the ball to A is 2 by 3 and C will throw the ball to B is 1 by 3. Now the states can be described as the A will throw the ball to B, it has probability, its probability is 1. B throw the ball to C, it has probability 1. Now the C has 1 by 3 probability, it will throw the ball to B, and with 2 by 3 probabilities it will throw the ball to A. So all the states are reachable here, from A to B, B to C and C to A. Similarly B to C and C to B from all other states. So the chain is irreducible. So this chain cannot be reduced because all the states are reachable. Now let us talk about another example. In this example, at time t is equal to 0, you have $20. If you bet $10 and you bet $10 each time in a gamble, you win with the probability of 0.3 and lose with the probability of 0.7. If you have $0 or $40, then game is over. So you play a game, you have $20 at the start. So initially you have $20 and you bet $10 in each gamble. So the probability of success that you will be win is 0.3 and you will lose, that is 0.7. So if you reach $0 or $40, then game will be over. So let's suppose X of t is the money you have after each gamble. So at time t is equal to 0, when time is 0, so the initially you have $20. So when you start, initially you have $20. So the probability of success is 0.3. So you will move from $20 to $30. So and the probability of failure is 0.7. So if you lose, that has probability 0.7. So if you lose $10, you will reach next state where you have $10. Now suppose if you have $10, then if you win, you will move to this state, to 20. So here the probability is 0.3. So if you lose, then you will reach here. So here when you have a $0, so then the game will be over. So the next state again will be the $0, so it has a 1 probability. If we move here, so if you have a $20 and you win, so you will reach in this state here. It is a $30. So if you lose again, you will move to this state or win. In this case, you will move to this state. Here you have $40. When you have $40, then game is over. So in this case, the probability would be 1. So now I define the state. This is 1. This is state 2 or 20. This is state 3. This is state 4, and this is state 5. The state transition probability matrix can be defined as, so if I start from state 1, so here is the state 1. So here at when you have a $0, you have probability 1. So you will stay at this state. So I can write at here the probability is 1 when when I is equal to 1 and j is equal to 1. So in this transition probability matrix, so here the probability is 1. So for next state, the probability is 0, here 0, 0 and 0. When you are at state 2, so here you have probability of failure, you can say, and you can lose the gambling, so you can move to first state. So here the probability is 0.7. Or if you win, then you will move to the state 3 where you have probability 0.3. For remaining, it is 0. Now you are at state, if you are at state 3, so at state 3, if you win, you will move to the state 2 with the probability 0.7. If you lose, if you lose, then you move to the state 2 with probability 0.7. If you win, then you move to the state 4 with the probability 0.3. So for state 4, here the probability is 0.3, and for state 2, here the probability is 0.7. So for other probabilities are 0. If you take the sum, then the probability of this row would be equal to 1. Now you are at state 4. If you win, So when we are at state 4, so it has a probability that if you lose, it has the probability 0.7, so we'll move to the state 3. If you win, in that case you will move to the state 5. So for state 5 it has a probability 0.3, and for state 3 it has probability 0.7. So the total sum of the probability is 1. So when you move to the when you are at state 5, so it has a probability 1 that it will stay at 5, because at $40 the game will be over. So this is the transition probability matrix. Because we start at state 3, so the initial probability हम लिख सकते हैं कि क्या थी हमारे पास. इनिशियली हमारे पास $20 थे. You have $20, so the initial probability can be written as Q is equal to because you are at state 3, so it has one probability remaining, 0. Now let us move to another example. A state transition diagram. This example is taken from your textbook. A state transition diagram of finite state Markov chain is a line diagram with vertex corresponding to each state and a direct line between two vertices I and j. If the p sub ij is greater than 0 in such a diagram, if one can move from state I and j by path following the arrow, then I to j, the diagram is useful to determine whether the finite state Markov chain is irreducible or not. To check for the periodicity, draw the state transition diagram and classify the state of the Markov chain. The following transition probability. We have given these transition probability matrix. So in first case, so we can say that here we have three states. I can say state A or so states can be drawn as in this case when for this transition matrix, so when we were at state 0, we have 50% probability to move to state 1 and 50% probability can move to state 2. So when we were at state 1, it has 50% probability can move to state 0 and 50% probability can move to state 2. And when you are at state 2, you can move to state 1 with 50% with 0.5 probability and state 0 with 0.5 probability. Now let's talk about second transition matrix. In this case, when there are 4 states, this is state 0, this is state 0, this is 1, this is 2, this is 3. When you are at state 0, you have 0.5 probability you will move to state 2, and 0.5 probability you will move to state 3. So here we can see our transition matrix 2. When you are at state 0, 50% probability you will move to state 2, and 0.5 probability you will move to state 3. When you are at state 1, you have the probability of 1 that you will move to state 0. So here when you are at 1, you have 1 probability. Here is the 1 probability. It shows it has 1 probability it will move to the state 0. Then again, when you are at state 2, you have 1 probability that you will move to state 1. So here is state 2, and you move to the state, and it moves to the state 1 with 1 probability. So in this row, when you are at state 3, you move to state 1 with 1 probability. At state 3, move to state 1 with 1 probability. Now, taking into account the third transition table matrix, so here this is state 0, this is 1, this is 2, this is 3, this is 4. There are 5 states. So we have 5 cross 5 matrix. So when you are at state 0, it means that you have probability you will stay at state 0 with 0.3 probability. You will move to state 1 with probability 0.4, and you will move to state 4 with probability 0.3. So the total sum of the probability is 1. So when you are at state 1, you will stay at state 1 which has 1 probability. When you are at state 2, you have probability 0.6 probability that you will move to state 3, and with 0.4 probability you will move to state 4. When you are at state 3, you will move to state 4 with 1 probability. When you are at state 4, you have probability you will move to state 2 with 1 probability. So here in this transition diagram, state transition diagram, when you are at state 0, you have 0.3 probability you will stay here, 0.4 probability you will move to 1, and 0.3 probability you will move to state 4, and at state 1 you will stay at state 1. So when at state 2, 0.4 probability you will move to state 4, and 0.6 probability you will move to state 3. So when you are at state 3, you have a probability that is 0.6, sorry, you have probability that is 1, you will move to state 4. When you are at state 4, you have a probability that you will move to a state 2 with the probability 1. So in first case, the state transition diagram of Markov chain with the probability P of part A is shown in the figure. It is seen that the Markov chain is irreducible and aperiodic. So in this case, it is not a periodic, it is a aperiodic. You can find it. For instance, we can get back to the state A in 2 steps by going from 0 to 1 and to 0. However, we can also get back to state 0 in 3 steps. In 2 steps and in 3 steps we can go to state 0. So in this case, the state for second transition matrix, the state transition diagram of the Markov chain with P of part B is shown in fig B. From fig, it is seen that Markov chain is irreducible and it is state diagram of fig B, it is quite obvious if we move from 0 to A, then to 1, then 1 to state 2, and then state 2 to state 0, or from state 0 to state 3, and then state 3 to state 1, and then it goes from state 1 to state 0. So it is a periodic with a period 3. Now let us talk about figure C, the state transition diagram of Markov chain with P of part C is shown in fig C. From fig, it is seen that the Markov chain is irreducible. So here you cannot reduce this state transition diagram, since the state 0 and 4 are do not communicate. So do not communicate, and the state 1 is absorbing. We can say that state 1 is absorbing here. So that's it. In the next lecture we will talk about the central limit theorem, and thank you.